Hello everybody and welcome to a chat from the engineering desk. Today we are going to talk about VSDs, the length of the cable between the VSD and the motor, the effects of the capacitance of the cable on the VSD and the motor, and what can be done to mitigate the consequences of having a long cable between the VSD and the motor. So over here on the screen we are looking at a VSD. There's your three output transistors, IGBTs. Well, it's sets of three sets of two. You got 6 transistors. You got one on positive and negative for your red, your white and your blue phase. Now over here I've drawn the cables, and the capacitors indicate what would effectively be your capacitance in your motor cable. Now, in the manufacturer's recommendation, they will generally say to you, after 100 meters of cable length, you need inductance, which would be an inductor in this point over here. It's at the VSD output. So it's between the VSD terminals and your cable that you need inductance. It's generally about 3 to 5% impedance that you need. Now let's talk about why this is bad when you don't have inductance and you've got capacitance, resulting capacitance from long cables. Now this capacitance, as a side note, varies depending on cable type as well. So it can become a problem before 100 meters, it can become a problem after 100 meters. Now I've got a chart here which is typical for the DC bus voltage of a 5 to 5 volt VSD. So your DC bus will be at about 742 volts. It's 5 to 5 times the square root of 2. Now let's take a look at this chart of mine. Our blue line over here is the output voltage of the VSD when the transistor turns on. Now that period over there between 1 and 2 is about a microsecond for your average VSD, in which the transistor goes from turned off to a fully conductive state. Now the next line is your current at that point if you've got a problem. So what happens is that current rises very sharply, and it actually rises way above the average value that's going to be after that because of the capacitance. And that's a very bad thing, because what happens is that you're drawing excessive amount of current through your IGBT while it's in a partially conductive state, and that in the long term or even the short term results in the IGBT burning out because of the heat being dissipated in the junction during switching. And that's a bad situation for the VSD. That leads to failure. Now there's a secondary complication, and that is effect on the motor. You get what's called overshoot of your voltage pulse at the motor terminals. That's the grey line. Now in this case it can easily be 3 times your DC bus voltage. You can see over 2000 volts at your motor terminals after the IGBT has turned on, and then there's some oscillation and it settles down after that. Now that's bad, because that causes insulation failure in your motor, because that sharp rise in voltage accompanied by the fact that it's such a high level causes corona discharge. You can easily at this point, without inductance, be within your corona inception voltage area depending on conditions and motor construction type. So that's another big problem, is that your motor is going to fail as a result of that. Now, if you have the inductance at your output, look at that light blue line, that's the one right at the back. That's what's going to happen to your current. It's going to gradually come up and it's not going to overshoot. So look at the difference between that line and that line of your current. Now that's current flow through your IGBT while it's switching. So note the big difference that it has on the IGBT and the resultant heating of your IGBT during switching. Because most of your IGBT losses are during this period when the switching happens. So if you haven't got inductance and you've got long motor cables, big problems. So what you're ideally wanting is that nice gradual curve of the current on the IGBT as it switches. Now the recommendation is at 100 meters you need inductance. This doesn't mean that you haven't got a problem before then, because this is a linear progression. So at half that distance you'd already got half of this problem. So, and depending on the type of cable, you could already have this at a much shorter distance. If it's a flat trailing cable, for instance, they are terribly capacitive. So that's a story worth having inductors on the output of the VSD. There's other benefits as well. If you've got thermal overloads connected on the output of the drive, if you've got multiple motors running off it, you don't want to subject that thermal overload to that either, because it causes heating. So you need inductance. What else was there to talk about? I think that was it. And of course, if you were to experience a short circuit or an earth fault of the cable at this point, the inductor is going to give the drive a good chance to detect the overcurrent condition and turn the IGBTs off. Without the inductance, that current comes up fast and it can destroy things. So an inductor is another sort of safety buffer, as it were, for phase to phase or phase to earth short circuits or faults on your cable or your motor. So consider an inductor and insurance policy as well. And they add maybe 5%, 5 to 10% to the installation cost of the VSD. Inductors are not expensive, and provided your panel's not too tight, there's usually room for it as well. They're not too big generally either, or it doesn't need to be in the panel, it can be outside in its own little box. And they don't add much in terms of losses to the system either. And yes, there's a little bit of noise coming off them because they're magnetics, but a well-made inductor is not too noisy. So those are the two considerations when adding a conductor, is that there's going to be some heat and a bit of noise, but it's not terrible. And that concludes our talk on inductors on VSDs. I hope that it was interesting, made sense, gave some insight, you learned something from it, and have a wonderful day further. We'll see you here for the next talk. Cheers.